Problem number 4 states, one mode of vibration of the CO2 molecule has an effective value of K equals 1400 newtons per meter. The frequency of the vibrations is F equals 7.0 times 10 to the 13 hertz, and the molecule has a total energy of vibration of U equals 4.7 times 10 to the negative 20 joules. So they want us to find out the effective mass as well as the amplitude of the vibration. So started out by just listing the variables given to us. So we have our spring constant K equal to 1400 newtons per meter, our frequency, and our potential energy. And they want us to find the effective mass and the amplitude. So just to kind of visualize what's going on here, we can think of our carbon dioxide molecule as a mass on a spring, and it's oscillating between negative A and A. So 0 to A is the amplitude, and then that negative A to A is the total energy of the molecule oscillating. So we can also draw a little energy diagram here. So yeah, from negative A to A, we have our total energy up here as 4.7 times 10 to the negative 20 joules, and then our potential energy is going to be decreasing as we approach 0, as our velocity is in the negative approaching 0, and then it increases back up once the velocity is positive. So right here at negative A and at A, the energy is purely potential. So yeah, that just kind of helps visualize the potential energy and kinetic energy in the system as we are moving in our oscillations. Okay, so now we can find the mass using this equation here. We can find the mass using the angular frequency, as well as the spring constant, and we know that the angular frequency is equal to 2 pi times the frequency, so we can just plug that in and we get our angular frequency equal to 4.4 times 10 to the 14 radians per second, and then we can just plug that in to this equation to find the mass. So just rearrange that. The mass is going to be equal to that spring constant divided by the angular frequency squared. Plug in those numbers, and we get our effective mass equal to 7.23 times 10 to the negative 27 kilograms. Teeny tiny. And now we can find the amplitude using our equation for energy. So we know total energy is equal to that maximum potential energy, which is equal to 1/2 of the spring constant times the amplitude squared. So since we have U and we have K, we can just rearrange that to find our amplitude. So just plug in those numbers. A is equal to the square root of the potential energy divided by half the spring constant, and yeah, we end up with the amplitude equal to 8.19 times 10 to the negative 12 meters. And this all ties into what we're learning in chapter 15 about oscillations and energy and simple harmonic motion.